Hello everyone, I hope you all are well and making progress in life. Here is Priyanshu and welcome to the Infinity Mind. So today I will be solving the problem find nth root of m. So the problem statement says that we are given just two numbers n and m and our task is to find nth root of m, and if the root is not integer then return -1. So we can see in the input we are given n and m and we have to find nth root of m. For example, n is 3 and m is 27. So we can see that if I take the example number 1, n is equals to 3 and m is equals to 27. So we have to find the cube root of 27. So cube root of 27, we all know, is 3. So the answer should be 3. But how we will find here? How we can write algorithm so that we can directly find nth root of m? So with the brute force, we all know that we should start from 1 and multiply 1 exactly n times, and similarly, and if it is equal to the m, then we can say that yes, we have found our answer, that this 1 is our answer, because if we multiply 1 n times, it will give m. Similarly, we will, but here, if we multiply 1 3 times, in this example, if we multiply, but we can see here that if we multiply 1 here 3 times, so it will give 1. So it's not equal to 27. So it means cube of 1 is not 27. So we will move forward to find, go and do the similar for 2. And now we will multiply 2 n times, and we will check is it is equal to m, and if it is equal to m, we can say that yes, we have found. But in this case it was not, and here if we multiply 2 3 times, that is cube of 3, this will be 8, which is not equal to 27. So we will say that no, 2 is also not our answer. And similarly, we will keep doing this, and when we will multiply 3 n times, so if we multiply 3 n times, that is 3 times, so this will be equal to m, and this will be answer, because 3 times multiplied will give 27, and we can see that 3 is our answer, because cube root of 27 will be 3. And so starting from 1 till where we should keep multiplying. So at max we should keep multiplying it, keep going up to m, because we have to find answer m. So in the worst case, n can be 1. All right. So the answer will not exceed m. So we can just try multiplying m n times. So we can use a for loop from starting from 1, then 2, then 3, and going up to m, and check if we multiply this 1 n times, 2 n times, 3 n times, does it give m? When it will give m, we can say that this ith I is our answer. Let's say if I start I from 1, then I can say I is my answer. So but we can see that if we try to go I from I is equals to 1, and we try to move I is equals to 1 to m, this will take linear time complexity of big O of m. But we know that we have to just multiply 1 n times, then go to 2 n times, then go to 3 n times, and search that if this multiplications uh, turn out to m. So why cannot we just instead of doing a linear algorithm, why we cannot use binary search? So instead of starting from one, what we can do, we can start from we can apply binary search, and this way we can save our complexity from big O of m to big O of log m. All right. So just simply we will do mid. We will find mid and check for mid, and if we multiply mid n times, uh, then if it is coming m, we will see that this is our answer, and we will return. And if it is if multiplying mid n times, if it is coming larger, it means our answer is if we multiply n times and it is giving a larger answer. Let's say mid is mid to the power n is giving a larger answer. It means mid to the power n is greater than m. So it means that mid we are multiplying mid, let's say 4, we are multiplying 4. All right. So which is greater than, obviously 4 cube is greater than 27. It means we have to go backward. So we can just say that now we have to check in the back direction. And if let's say this 2 into 2 into 2 multiplied n times is less than m, so we can see that our answer is forward. All right. So we all know this binary search approach. We can solve uh, through this. All right. So if I go and implement this, so what I was doing, I was uh, I was just applying binary search, and my uh, first task was to start a loop. So instead of starting a loop, I was saying that I will use binary search. So I can say that my low will be 1, and my high will be, and I have to go till m. And while you all know the template of binary search, every time, first of all, I have to find mid, and mid we all know what is mid. This is low plus mid by 2, or low plus high minus low by 2. All right. Now I have to go and find the value. I will store it in long. The value, the power of mid raised to the power n. I have to find mid raised to the power n, and now I will check that if this value is equal to m, so we can say that we have got our answer, and we should return directly the mid. It means that we are multiplying mid n times and it is giving us m. So you can see that this is our answer. Else if the value which we are getting can be, let's say, greater than m. So if it is greater than m, it means the answer is backward. So we should go backward. And for going backward, we all know we should make high mid minus 1. All right. And in the else case, when value is less than m, I should say that I have to check forward. So in this case, low will be mid plus 1. And at last, if nothing returns, I can say that I have not found any root here. It means the root is obviously not integer. Root is not integer. So if any from starting from 1 to m, from 1 to 3, any integer does not give us answer, it means there is any uh, a double value or floating value, we can say that will be our answer. That decimal value will be our answer. But in that case, we have to return minus 1. So if nothing returns, I will return minus 1. And now I have to just write the function for finding the power. So we can simply use the I am writing the function. So what I have to return here, I have to return a long value of power of mid. Uh, Here what I have to do, I have to find a raised to the power b. So I am writing a raised to the power b. So we all know how to find a raised to the power b. We can either write a simple for loop multiplying a b times, but this will take big of n time complexity. But if I we if I write the code binary exponentiation, and I hope I know you all know about binary exponentiation. If you don't know, you can just check my video also or any other video on internet or Google. It binary exponentiation. It finds a raised to the power b in big O of log b time. All right. So I will just write the binary exponentiation code. This binary exponentiation is another problem we have solved on lead code, that is pow x raised to the power n, and you can check it out. So I'm writing that code only. So that code was nothing but if I have to find a raised to the power b, it will be I can write it at a square raised to the power b by 2 if b is even, and if b is odd, then this will be nothing but a multiplied by a raised to the power b minus 1 by 2. This will be our code. All right. So yes, we can see that here 2 and 2 will cancel, and this will give a raised to the power b. And also 2 and 2 will cancel, and this will give a raised to the power b minus 1, and here a raised to the power 1, and if we combine this will give a raised to the power b. So I can just store my answer as long answer is equals to 1 and 1 ll, and now I can just write either a recursive code for this or a iterative code. I'm writing iterative code for simplicity. So I will go while b is greater than 0. So if first of all I will check if b is even. If b is even, what I have to do, if b is even, I have to just divide this b by 2. B will be divided by 2, and in this case answer is multiplied by answer is squared, so answer is multiplied by answer. And in the else case, if b is odd, so I have to do just multiply answer with a, and decrease b by 1. All right, so I will multiply answer with a, and decrease v by 1, and at last I can just return the answer. And one optimization I can also do, let's say while finding mid raised to the power n, and if it exceeds m, I can simply say that uh, it is not possible because constraints are very high, 10 raised to the power n, and let's say n is 30 and m is 10 to the power 9. So let's say n is 30. All right, and m is 10 raised to the power 9. All right, and I am on 10 raised to the power 9, and I have to find 10 raised to the power 9 raised to the power 30. So this will be around 10 raised to the power 270, and this cannot be stored in our long. So I will say that whenever I am multiplying, and if my answer exceeds m, I can just simply say that return this, what do we say here, mid plus 1, or I can just say that return the, it means that it is exceeding m, it means the answer is backward. So what should I return in value such that I have to find it backward? So the value should be greater than m. So I can just simply return m plus 1. Alright, and I should also pass m here, int m, and here I will pass m. And now I think we are good to go. And if I submit this, first I should compile this and check if we are able to pass sample test cases. So something is wrong here. That on the line 36, return minus 1. So this should be inside this bracket. And if I submit this, if I just compile and run and check it, and if I submit this and check whether we are able to pass all of these cases or not. So we have made some mistake. We don't have to make answer, uh, we don't have to square answer, we have to square a. So that's the case. Actually, I mostly get the wrong answer while writing the iterative code, because this recursive code is very transparent, but iterative code is very, uh, it saves our stack space complexity. The problem was just when b is even, we have to square a and divide b by 2, and when b is odd we have to multiply the answer by a and decrease b by 1. Else if we write any recursive code, we can just simply write these things. If b is even, we can just square a and divide b by 2. We can actually call a square and b by 2, and if b is odd, we can actually call, if we can actually multiply a and call a square and b minus 1 by 2. All right. So yes, we have solved this problem now successfully. And if I talk about the time and space complexity, so that uh, we can see that this this binary search, we are applying from 1 to m range. So time complexity will be big of log m, and we can see that in every problem, we in every iteration, we are finding power also, and for finding power I'm using binary exponentiation. So this will take log of and time complexity. So we can say that our time complexity is big of log m into log n, and space complexity, we can say that we are not taking any space, so space complexity is big of 1. So I hope you understood. Thanks for watching. Till then, keep learning and keep upgrading yourself. See you in the next video.